to discuss about the architecture of TMS320C67XX DSP processor. Okay, so we are going to discuss about TMS320C67XX. Okay, so this is a DSP processor, that is digital signal processing processor it is. So this DSP or digital signal processor is from Texas Instruments, and it is used for processing of digital signals. Okay, so they are used for processing of digital signals, and this is the architecture of the DSP, that is a digital signal processing architecture, or DSP architecture is this. And this is a very sure question in most of all the DSP exams. In DSP exams, at the end you have to study one architecture, and in most of the syllabus, in most of the universities, this architecture is being kept, and it is a 100% sure question. Especially if you talk about the K2 exams, this question I have seen from a lot of years, that is previous year question papers, and this question is a 100% sure question in all those question papers. So if you are going for the DSP exam, please do study this topic. So we are going to discuss this topic today in an exam point of view. So this is the architecture you need to draw in your exam paper. Okay, so this is the TMS320C67XX architecture, which consists of a memory, that is program memory and data memory. And also this is having a CPU, and this CPU, that is C6000 CPU it is. That means this CPU is common for all the C6000 families. So this C6000 family, it consists of C6200, 6400, and likewise a lot of versions are there for the DSP. That is for the digital signal processor. A lot of versions are there which is coming under this family, and the CPU is common for all those families. So it is a common CPU, and this processor is having memory, CPU, data memory, then DMA, that is direct memory access and external memory interface, and also various peripherals. Now we are going to see what are the function of all these components or all these blocks. Okay. So first, we'll talk about the memory. So there is a program memory and there is a data memory. So from the figure itself, it is clear that the memory is organized as separate. There is program memory and data memory is organized as separate. And this CPU is consisting of a lot of units. We'll discuss about it. And also there are additional peripherals, timers and ports. And also there is DMA. Now, first, we are going to discuss in detail about the CPU. Later, we will talk about the memory in more detail. We are going to talk in detail about the CPU. So, the CPU, what is the function of a CPU? CPU means central processing unit. So, it will be the center which is dealing with all the processings at the end. So, if you are going to process an instruction, the CPU will be fetching the instruction and the data, and they will be doing all the needed processings, right? So, here, this processing unit, which is a central processing unit, is having a, here the top there is a program fetch unit, then there is a instruction dispatch unit, then an instruction decode unit. So when a instruction need to be processed, what all things we need to be done? First we have to fetch the instruction, then we have to dispatch the instruction, then we have to decode the instruction. That is, first we are going to fetch whatever instruction is to be processed, we are going to fetch that. Then we are going to dispatch this instruction to the various units. Then we are going to decode, that is whatever instruction, what is that written in the instruction, we are going to decode it. That is what we have to do. We can only find by decoding. So decoding is done. Then what will we do? Or then what the CPU will do? Then it will process, right? So these are the three basic units for fetching, dispatching and decoding of the instruction. So from this program memory, all the required instructions are being taken. From the data memory, all the required data will be taken. Okay. Now inside the CPU, if you see, there is two data path A and data path B. Okay. Anyway, if you are not able to clearly see this figure. Don't worry, I've included the detailed figure in the end of this video. That is a image I have inserted. Okay, so don't worry about it. Now let us please listen. Okay, so there are two data paths inside the central processing unit. Now don't confuse the data path with a path of flowing of data. It is not a path of flowing of data. Data path means data path is equal to processing unit. So we call a processing unit by the name data path. If you see any of the IEEE papers or any of the conference papers, you will be able to see this name called data path. Data path means processing units. We call them as data path. So the core processing units are called data path, and the CPU core consists of two such processing units. Okay, there is a data path A and there is a data path B. The data path A consists of register file A and data path B consists of register file B. Now the register file, each of these register file consists of 16 registers each. That is, this register file A consists of 16 registers, and this register file B consists of again 16 registers. So total there is 16 plus 16 is equal to 32 registers are there. And each of these registers are 32-bit size. Okay, so there are 32-bit size registers totally within the register file units. Okay, now after the register file, you can see there is .L1, .S1, .M1 and .D1. Now these are the functional units. We know that at the end, the processing unit is doing its processing with the help of arithmetical and logical units and also multiplication units, right? So here you can see there are 4 such functional units along with each data path. There are 4 with data path A and also the same 4 with the second data path B. Okay, so what are these functional units? This L1, S1 and D1 for data path A are ALUs, and also this L2, S2 and M2 are ALUs. So there are how many ALUs total? There are 1, 2, 3 plus 1, 2, 3 total. 6 ALUs are present. Okay, so there are total 8 functional units for A and B. If you take the sum total of functional units, there are totally 8 functional units, and out of which 6 functional units represent ALUs. That is, they perform arithmetical and logical operation. And if you see, there is a .M1 and .M2. So this .M1 is a multiplier. So there is one multiplier for data path A and next multiplier for data path B. Okay, so out of this total 8, there are 2 multipliers and 6 ALUs. Okay, 2 multipliers. So this is the functional unit details. And these functional units are actually doing the addition, multiplication, division, subtraction, all these functions. We know that at the end, if you're going to process an instruction means we'll be performing any of these, right? Addition, subtraction, multiplication or division. That at the end of the decoding an instruction or processing an instruction is equal to performing any of these operations, right? So this performance or this operation is done with the help of this functional units. I hope this is clear. Okay, so that is all about the data paths of the DSP processor. Now, let us move on to this area. So this area is consisting of all the control registers, control logic, testing area, emulation and also the area for handling of the interrupts. We know that the DSPs will handle interrupts also. So the interrupt processing, the test, emulation and the control units, we need some control instructions and control logic for the correct operation of this CPU, right? And all those things are kept here. So it consists of control registers, control logic, test, emulation and interrupts. Okay, so this is all about the central processing unit of the CPU. Central processing unit of the DSP. Okay, so what all things are present? There is a program fetch unit, there is an instruction dispatch unit and instruction decode unit. So after these 3 operations, we have the decoded instruction. Now we need to actually process that instruction. For that, we first we have decoded the instruction. Now we will take the data from this data memory and we will actually do the operation inside the data paths. Okay. So I hope this concept is clear to you. And the controlling and the coordinating of these operations are done with the help of the control logic, control registers and all. Okay. Now, so we have talked about the CPU here. And if you see here, there is a power down unit. Now, what is the function of the power down unit? Power down unit is actually is helping to reduce the power of the DSP. That is, the DSP will be consuming a lot of power and the DSP will be operating in a particular clock rate. So, the power down unit, what it will do is, it will reduce the clock rate and it will try to reduce the power consumption. And if the DSP is operating in some power saving mode, this power down unit will be active. Okay, so that is about the power down unit here. So I hope this portion of the DSP architecture is clear. Okay, next let us move on to this portion. There is a DMA here and there is a EMIF. What is a DMA? So I am going to draw a rough figure of DMA. Okay, so there is a memory. There is a memory. There is a CPU. And consider that some register need this memory to be accessed. That is, some register is trying to access this memory. So what is the normal way? The register will first ask the CPU and then the CPU will grant permission to access the memory, right? So this is happening. Normally the registers cannot just directly go and take data from the memory. It has to first ask the CPU and then CPU gives permission to access memory and then only the registers can access. That is, accessing means reading or writing from the memory is only possible. So that is the case. But what will happen if a DMA is possible? DMA means direct memory access. Direct memory access means here the register can access the memory without asking the permission of CPU. That is, we call this as without intervention or without the influence of the CPU, the register can directly access the memory. And this accessing is controlled with the help of Direct Memory Access Controller or DMA controller. Okay. So that way of accessing or that type of memory access is called a direct memory access. So in this DSP architecture also, the direct memory access is possible with the help of a DMA unit. And this DMA unit is having a DMA controller. Okay. So that is all about DMA. So if you see here, see, this block is directly connected to the program memory and it is directly connected to the data memory without connecting to the CPU. This is the CPU, right? So this is the CPU and without any connection with the CPU, directly there is a connection between the program memory and the data memory, which is telling us that direct memory access is possible without the intervention or without the influence or without asking permission from the CPU. So I hope that is clear. Next, there is another unit, there is another word given here. EMIF means external memory interface. Means here, without using or in addition to the internal memory, we can also add some external memory to this DSP. That is SRAM, SDRAM and SBRAM. Various other memories can be added or can be accessed within this digital signal processor, and this accessing of external memory is made as with the help of external memory interface, that is EMIF. And during the external memory interface or when external memory access is happening, this program memory and data memory, which is kept as separate, will be unified together. Okay, so that is happening for a EMIF. Okay, so that is all about the DMA and the EMIF. Now, what is about that is, let us talk about the program memory and the data memory. So here if you see, the program memory / program cache means this program memory can be sometimes used as a program cache also. Cache memory means the fast accessing memory is called cache memory or the easily available memory is called cache memory. So this can be used as cache also. So here the data memory can also be used as cache. And this program memory is having 32-bit address and 256-bit data. And here the data memory is having 32-bit address and 8, 16 or 32-bit data. That is, the data bits or the data size can be varied for data memory as 8, 16 or 32-bit. Okay, so this is all about the program memory and the data memory. The memory organization is like this. And there are several additional timers, serial ports and various other peripherals for the this DSP architecture. We are going to discuss that in detail. Okay. So the C6000 family follows the VLIW architecture. VLIW means very large instruction word. That is, these DSPs are able or capable of processing very large instruction words. And what they will do is they allow parallel processing of these instructions. What the VLIW architecture is actually doing, they are going to club all the instructions together and form a large word of instructions. And for processing, what they do is they process these instructions parallelly. Okay. So this type of architecture is called VLIW architecture, and this DSP processor, that is C67XX DSP processor, and this family, that is C6000 family, follows VLIW type of processing of instructions. Okay, now we are going to see in details about the various peripherals, timers and also some ports. We are going to discuss about the peripherals, various peripherals. First one is a DMA controller and extended DMA controller. So as I said, the DMA controller is used for making DMA, that is direct memory access, possible. And this direct memory access is controlled with the help of a DMA controller, which is not a CPU, it is a separate unit. Okay, so this DMA controller is allowing 4 channels for DMA passing, and these 4 channels are programmable, and there is a one auxiliary channel which is not programmable. Okay, so total there is 5 channels possible. And there is an advanced version of the DMA called the extended DMA controller. Now the function of this extended DMA controller or extended DMA is similar to that of DMA. The difference is that it is offering 16 programmable channels for transferring of memory or DMA access. Okay, so the DMA controller, if simple DMA controller is used, 4 channels programmable and 1 auxiliary channel. If extended DMA is used, there is 16 channels. Okay, so while explaining about the DSP architecture of C67XX, if you mention about these things, you will get good score. Okay. Next thing is HPI port. HPI means host port interface. Now, what is the function of this host port interface or HPI? Consider that if this DSP processor, that is this C67XX DSP processor, is used along with some other host processor, and if this host processor wants to access the CPU of this C67XX, then it is possible with the help of a HPI port. Okay, so this is a dedicated parallel port which helps the interaction between the host processor and the CPU of the DSP architecture or this DSP. Okay, which is called the HPI port. Now we can also use any other serial port or any other or even EMIF we can use for this access. But this HPI is a dedicated port or a part for the communication or synchronization between these two, that is host processor and the CPU. Okay, so that is the HPI. HPI is host port interface. Next is expansion bus. Expansion bus. Expansion bus can be used in replacement as EMIF, that is external memory access, or HPI ports, that is host port interface, can be replaced with the help of an expansion bus. And this expansion bus, I'll write it in the top. This expansion bus is having 2 modes of operation, asynchronous mode and synchronous mode. In the asynchronous mode, it acts as slave, and in synchronous mode there are two modes possible, slave and master mode. Okay, so the expansion bus has two modes of operation, synchronous and asynchronous mode. Next one is multi-channel buffered serial port, that is MCBSP. Okay, so this is a multi-channel bus or a multi-channel port, multi-channel buffered serial port, and also it is used for during the direct memory access. When direct memory access is happening, some buffered samples can be stored in the multi-channel buffered serial port. Okay, and also since it is multi-channel, it is allowing a lot of network protocols or algorithms can be applied to the multi-channel buffered serial port. Okay, so you should be mentioning about these all peripherals and devices and serial ports. Okay, so this is all about the ports and the peripherals. Now about the timers. The timers, there are two timers present in this C67XX architecture. There are two 32-bit timers. Okay, so these timers, the functions are, they are used for timing of events, they are used for generating of counts, they are used for generating of pulses, and when the direct memory access or EDMA is used, they are used for synchronization purpose, and also they are used for interrupting of CPU. They are used for generating of interrupts also. So these are the functions of the timers, and there are two 32-bit timers present inside the C67XX DSP architecture. Okay, so this is that is all about the timers. Now let us see some additional features about the DSP architecture C67XX. Okay, so now let us see some additional features about the DSP architecture C67XX. Okay, so the first feature is that the hardware of this DSP architecture support single precision and double precision format. Single precision means it supports 32-bit and double precision means 64-bit floating point operations. Okay, so this supports single precision and double precision for floating point operations. Single precision means it allows 32-bit operations and double precision means it allows 64-bit operations, that is floating point operations. Okay, and also as I said, it follows a VLIW architecture, and this VLIW architecture for this particular C67XX processor process 8 instructions per cycle. Okay, so it processes 8 instructions per cycle, and also while multiplication is performed, that is a 32 into 32, we know that all the registers are 32-bit in size. So if a 32 into 32 is multiplication is happening, the result can be either 32-bit or the result can be 64-bit. Okay, so these are the some features about the C67XX DSP processor. And if you are writing this in your examination, first you have to draw the figure neatly, because if you draw the figure, more than half of the marks is obtained if the figure is correct. That is, if the question is asked, normally the question will be asked for 15 marks or more than 10 marks in any way. So if the mark is 15, you will be getting up to 13 marks if the architecture figure is correct. Okay, so first you have to study the architecture figure correctly. You have to draw it neatly, then try to explain about the various parts in the figures. Not very in a very detailed manner. You have to write a only brief description about each of these items. Okay, so my request is that if you are going for DSP exams, don't ever skip the architecture, because it is a 100% sure question. As I said, I have not seen any question papers without this architecture. So that is why I have tried to include a video about this architecture, because a lot of people was requesting for the architecture, because a lot of people are going to write DSP exams. So I hope that this video was useful for your preparation. If yes, please do give it a thumbs up, and if any of your friends is preparing for KTU DSP examinations, please do share this video with all of them. And if you want more videos, please do subscribe to the channel. Thank you.